everyone, thank you so much for clicking onto the video. Today's learning objectives are all to do with chromatography. So first we're going to look at the interpretation of one-way TLC chromatograms in terms of RF values, and then the interpretation of gas chromatograms in terms of retention times and the amounts and proportions of the components in a mixture. So now we're going to talk about chromatography. Now, chromatography can be used to separate and identify the components in a mixture. And separation depends on the balance between solubility in the moving phase and retention by the stationary phase. And chromatography describes a whole family of separation techniques, and they all depend on this principle that a mixture can be separated if it is dissolved in a solvent, and then the resulting solution, now called the mobile phase, moves over a solid, which is the stationary phase. So we're going to look at three types of chromatography. The first is thin layer chromatography, which you've already seen, but we're going to quickly review. And this is where a plate is coated with a solid and the solvent moves up the plate. And the second type of chromatography we're going to look at is column chromatography. And this is where a column is packed with a solid and a solvent moves down the column. And then the final type of chromatography that we're going to look at is gas chromatography. And this is where a column is packed with a solid or with a solid coated by a liquid, and a gas is passed through the column under pressure at a high temperature. And so the first few things that you need to know about chromatography is that we have the existence of a mobile phase and a stationary phase. So the mobile phase is what carries the soluble components of the mixture with it. And so we have the rule that the more soluble the component in the mobile phase, the faster it moves. And we say that it's got a higher affinity for the mobile phase. And the mobile phase is usually the solvent. So if we were going to look at paper chromatography, for example, the mobile phase would be the solvent because that's what carries the soluble parts of the mixture up the paper. And so if it's got a higher affinity for the mobile phase, or if it's more soluble, the component, then the faster it moves, and so the higher up the piece of paper it will be at the end. And when we look at the stationary phase, this will hold back the components in the mixture that are attracted to it. And so the more affinity a component has for the stationary phase, the slower it moves with the solvent. And that's because it's more attracted to the thing that's not moving, basically. So if we were looking at paper chromatography, then the stationary phase would be the paper because the paper's not moving. And this is what's slowing some components in the mixture down and not letting it move with the solvent. And so that's why we have that if we've got a higher affinity for the stationary phase, then it will move slowly, more slowly with the solvent. And so at the end, it won't be as high up the paper as other things. And so a particular component in a mixture can be identified by what we call its retention factor value, or its RF value. And this is fixed for a component in a mixture where the chromatography is performed in a specific way. And one really important thing to know is that the RF value for a particular component will be different depending on which solvent you use. And now we're going to look at the last chromatography technique that you need to know. So this is gas-liquid chromatography, or gas chromatography. So this technique is actually one of the most important modern analytical techniques. And the stationary phase that we use is a powder which is coated with oil, and this is either packed or coated onto the inside of a long capillary tube. And this tube can be up to 100 meters long and less than half a millimeter in diameter. And the mobile phase is usually an unreactive gas, and examples of unreactive gases are nitrogen or helium. So what happens is that after injection, the sample is carried along by the gas, and the mixture separates as some of the components move along with the gas and some are retained by the oil, each to a different degree. So the components which move along with the gas have a higher affinity towards the gas, so the mobile phase, whereas the things which tend to stay behind and are retained by the oil have a higher affinity to the stationary phase, and so they get left behind. And this means that the components leave the column at different times after injection, and so they have different retention times. So with gas chromatography, instead of working out RF values for the different components, we actually use retention times to identify them. And so the components which leave the column with a quicker time are the ones which have a higher affinity for this mobile phase. And so they move along with the gas, and so they exit first, compared to the components which have a higher affinity for the stationary phase, so the oil, the powder coated with oil. And so they get left behind a little bit, and so they'll exit at a later time. And various types of detectors are used, including ones that measure the thermal conductivity of the emerging gas. And various types of detectors are used, including ones that measure the thermal conductivity of the emerging gas. So how we analyze it is that we get a graph that looks like the one on the right. So we have the signal from a detector and then retention time on the x-axis. And so the area under each peak is proportional to the amount of that component. And so, for example, we can see that this peak here, it's got quite a large area under the graph. And so that means that we've got quite a lot of that component. And in some instruments, the components are fed directly into a mass spectrometer, infrared or NMR spectrometer for identification after all of the components have been separated. And this whole process is automated and also computer controlled. And as I said before, the identification of a component is done by matching its retention time. And this is with a known substance under the same conditions. And this is then confirmed by comparing the mass spectra of these two substances just to make sure that they match. And then finally, you'll need to know about some of the advantages of gas chromatography. So the first is that it's extremely sensitive, and then it can also separate minute traces of substances in foodstuffs. It can also link crude oil, which is found on beaches, with its tanker of origin by comparing oil samples. And it's actually best known for testing athletes' blood or urine for drugs. So on the right, we have a diagram of how gas chromatography would work. And so we have the long capillary tube, which has the stationary phase. So it's got that powder coated with oil. And so we've coated that along this whole tube. And then we've also got this carrier gas, which has gone into this tube. And so this acts as the mobile phase. So we have our mobile phase here. And we have the stationary phase, which is all throughout the capillary tube. And then the sample gets injected at the top here. And so it goes in this direction. So it goes down, and depending on whether it's got a higher affinity for the mobile or the stationary phase, it has a different retention time to another component. And so all the components get separated because some will have a higher retention, a higher affinity for the mobile phase, so they'll have quicker retention times, whereas the ones which have a higher affinity for the stationary phase, a larger retention time. And so at this detector here, this is where we obtain this graph of all the components and their retention times. And then we can compare retention times with, and then we can compare the mass spectra of this substance with the substance we think it is. So now we're going to look at how to interpret a gas chromatogram. So each component is detected as a peak on the gas chromatogram, and we can get two pieces of information from a chromatogram. The first is the retention time, and this is used to identify components present in the sample by comparing these to times for known components. So it's like the retention factor values when we look at thin layer chromatography. And then we can also look at peak integrations, which is the areas under each peak. And these are used to determine the concentrations of components in the sample. So the way we do this is firstly prepare standard solutions of known concentrations of the compound being investigated. And then we obtain gas chromatograms for each of these standard solutions. We then plot a calibration curve of peak area against concentration, and this is what we call external calibration, and this offers a method for converting a peak area into a concentration. And so if we look at the diagram on the right, we've run gas chromatograms for each of the standard solutions. So in this example, we have 4 of them, and then we plot a calibration curve, which is the relative peak area over the concentration. And so we can use this to convert a peak area into a concentration. So then what we do is we obtain a gas chromatogram of the compound we're investigating under the same conditions. And then we use this calibration curve to measure the concentration of the compound. So what we do is we basically go to the relative peak area, and then we draw a dotted line, for example, say the relative peak area was here, and so we draw a dotted line to the calibration curve and then draw a straight line down. And then this here would be our concentration of that component.